Hello, this is a video taken at a site in South Wales where we're creating a radial structure with RMD curved formwork, and I'm going to just cover a little few things that show how the first video is different with the second video. Okay, we put on the first video in YouTube for people to look at, and we've also put it on LinkedIn, so it can be found by entering this title, creating a radial structure with RMD formwork. Okay, this is how we do it, the second part of it. Okay, the task was that we had a 2 meters 832 radius shutter. That's from the center radius point out to the inside face of the 300 wall, and this is a complete half circle, so it starts at sort of 9 o'clock, goes around to 12 o'clock if we're talking in watch terms, and ends up at 3 o'clock. If we're talking in compass terms, its bearing is 270 degrees in this direction. It goes to 360 degrees there, which is basically 0, and then it goes from 0 to 90. So we're looking at the northern half of a circle. And what we're going to do is we're going to check various coordinates around here by using an instrument, a surveying instrument that's positioned out here in the distance, or out here in the distance. We can't get near to where we'd ideally like to be placed because of materials, etc. in the way. So we take two sets of readings, one to this side of the shutter, one to the other, and we compare them and figure out, by comparing, say for example, a bearing that we achieve here, an easterns and northerns with the easterns and northerns here, we'll get a result that shows the whole circle bearing, indicating where it is on the shutter, and the actual distance. And the distance we're looking for is 2 meters 812. So now I'm going to just show on the software that we use to test these results. We enter this surveyed values here in the table, east and northern, and once we enter them, they generate the model, the CAD model. So I then go to a function which allows me to click on the centre of the circle here, and I'm going to pick a random one of these readings here. So I'm going to go up to that one there, and if you look here, oh, this is quite surprisingly good. Our bearing there is 332, and we're looking for a horizontal distance of 2812. We've actually got 2809, so we now know that at that particular point at 332, which is about 11 o'clock if we're talking of on a watch, is within 3 millimeters. Let's have a look for one, let's see if we've got one a bit worse. I'll click on here and I'll go to this one. Right, okay, so we've got another reading here, and at these coordinates here that we've surveyed on the shutter, and we've come out with 2807. So we've picked on some good readings here. We did have some readings as bad as 15 mil, and we've done a slight tweak to the 15 mil, and it's probably somewhere in the order of 10 mil now when we've poured, and we'll check after it's been poured, but I don't think there's going to be an easy way of moving these after it's been poured. You really have to get it right first of all, because when you're trying to move afterwards, with the whole weight of concrete in there. So this particular reading here, we look at, oh gosh, we got 2812 and it's supposed to be 2812. Okay, so let's go to my field book and I'll show you how I've entered them, etc. So what I've done in my field book, you've got the date and the bits and pieces, and we've got the coordinates that I've entered. From these coordinates, we then generated a distance and a bearing to the centre line. So this is the distance. We're looking for 2812. In the first two cases, we've got 20 mil offsets, so we should be looking for 2832. So our errors are 25 mil less 20, which is 5. 31 mil less 20, 11 mil. Now all of these then are actually looking for 2812. So we've got 2807, which means it's 5 mil in undersize. 2797, which is 15 mil undersize. And you've got the location where it is. It's at 7 degrees. So we'd be expecting afterwards. We'd know where we're likely to have problems, if there were any, by these locations, because we won't be able to survey it again, or we could plumb survey it, etc. Right, so as you go down, as you can see, these are our results, and they're all pretty good. We're looking for see a bad one there, 12 mil, but all these are considerable. Now these are in relation to the true position, and we're now going to go out on site and just have a look at how it was done. So, off we go. The boys have just finished the concrete pour maybe 15 minutes ago, and the wagon has gone off site, and you can see where the shutter is in the distance. It's where the yellow jacket is sticking up on top of the scaffold. So the speed of the concrete pour is very important when you're doing this shuttering system, because it's a 3-meter high wall, and if we're trying to discharge, it actually takes about 8 meters of concrete, okay? So we can get an 8-meter concrete wagon in and complete it in one go, really. So if you bear in mind the driver wants to go after about half an hour, and the recommended sort of design is that we put in 1.5 meters cubed, wait an hour, and put in the extra 1.5 meters cube. There's a clash of interests there, so we've got to try to hit a happy ground. And we made a slight delay, but nothing like what was textbook. So this is where my instrument is positioned, and from here I survey a cup with a laser hitting the shutter. I've got to be careful that I actually hit the ply and not something else. I'll get the coordinate of where my laser is hitting. So I take a series of readings from one side, and I take a series of readings from the other, because the laser has to hit the shutter in such a way that it's not an acute angle, ideally a 90 degrees, but you can't get that. So, okay, let's go and have a look at the shutter. There's the shutter in all its glory. Okay, the first pour that we did on our other video showed how the same shuttering system was put on the bottom to a kicker. Well, it didn't even need a kicker if you don't want to. You can actually line it with a steel tape and a series of Hilti nails, and that's what we chose to do. So we had a centre radius point, and I set out a series of nails around the 180 degrees of the curve, and the boys tried to follow that. Before, the shutters were, as you see, they bent to a shape. Now that shape, they use a former to get the shape, and the former is on site. It's on a little table, and if you look across the site from where I'm standing, I'll try to line up. If you go through the centre of that compressor and look in the distance, you'll see the former there, and the curves that the shutter gets placed on them curves and bent and curved to that shape. Okay, so when the shutters come across, they're ready formed. They shouldn't ever be altered on site after that. They should fit perfectly. So when they were positioned to the nails at the bottom, we had a push-pull system that pushed in and out to get them onto the nail, and the top had a push-pull which plumbed the system. It's on another video in much more detail, so I won't go into it. On the top we have a system here now where we have to replicate the kicker, and so we basically follow the top of the existing wall, whatever shape it turned out to be, which was quite good actually. And we clamp onto that, and we get our level by adjusting on, if you look at these RMD strongbacks, at the very bottom of them there is an adjusting system for the height. So they were all put to the correct height. That's very important, you get it to the correct height. And then ideally then the shutter is all level, and it should work by aligning it in. Now it was lined in with partly with plumb bobs, partly with me taking the odd reading on it. It wasn't too intense work for either carpenters or me. You know, it's quite practical at working. And the way of controlling the in and out movement, if you look at the well, let's take a step back. The movement works a little bit like it's at the kicker level. We have a point where the shutter is fixed there. So if you pull out at the bottom, it pushes in at the top and vice versa, much like a seesaw. So it's a case of pulling out the bottom strong back, and then the top of the shutter will go outwards, or if you pull it in, it goes inwards. And the ideal dimension for it to be right is 50mm. So we go to the bottom here. Okay, that's where the adjustment is made. It's made at the bottom of the strong back, and the packing is just below the divvy dag. Ideally it should be 50mm, so that one there, as you see, is 45mm, which would indicate we had to pull the shutter inwards 5mm. And generally it all worked too well. We didn't fancy, when we had results like 15mm 1.5, we didn't fancy spending a lot of time on it, because we took the opinion that pulling one in affects the next one a little bit too much. So going along here, generally we've all got 50mm everywhere, because the reading of the original was very good, and that's backed up by the results that we had. So we'll have a look now at the back of the shutter. So just to go through it so anyone understands, it's that packing at the bottom of there causes this sort of cantilever effect at the kicker. The kicker doesn't move, and an outward movement at the bottom would produce an inward movement at the top. Am I got that right? Yeah, an inward, well, whatever, it's pretty clear. Okay, here's the back of the shutter. The shutter is supported at the back on stools, and these pack up to level, much like we had at the front. We had a system here. We just spirit level the top of them and check dumpy levels on them, and we give the chippies a level up to what looks level. Okay. One of the worries with placing the concrete too fast is that we might have had some grout loss or misshaping in the shutter. And if there was to be any, it's likely to be at that point where the shutter joins. If you see that dark rib in the concrete here, that was where we did the first pour. And what we noticed on this particular section of the first pour here is that at the bottom of it, because of the speed of the pour, we had a very small gimp. It looks a little bit worse maybe as I'm looking at it on the camera here. It actually works out, it's about 8mm. So so that we basically ended up with the bottom part of a wall 8mm thicker at one point, and then as we went up, because there's no weight on the top of the concrete, it's back to its normal correct alignment there. So when we've gone up there now, if that had replicated itself, we'd have expected that shutter to have given a bit of grout loss. It hasn't, and it's been very good in that respect, so there's no problems with it. One of my tasks now is to survey it after the pour, but I already realise that we're not going to be able to do much to it, although it's worth doing for the record, just to see. So I'll take about half a dozen readings each side now and see how the radius compares. Yeah. The system supplied by RMD is quite a good system. It worked quite well. A lot of heavy parts on it. Maybe not quite as modern as some of the other systems on the market. F-Core seemed to be quite a keen choice with some carpenters. System that I'm familiar with, although not familiar with the radius shutters, is the Perry system. That always seems to work quite well. But on a job like this size, where we got one simple task, and this shutter was uncomplicated to put up, and it did the job. So hope it's been a bit useful seeing how it's done. A little quick look at the rest of the job down here. Here we've done, here's a a great big 6 metre high retaining wall which retains the ground to the right of me and the ground level to the left of me, which is pretty much where I'm standing. So the inside of this is we're going to have gymnasiums and basketball and gymnastics and the like of that indoors, so it's a sports centre. The value of the contract is £3 million. So there we are. Yeah, the standard of work here is very good actually. They're very good tradesmen on here on that. So okay, back to the instrument now and take some finished results on that concrete wall. Hope you enjoyed the video.